Thank you. So I'll talk about the various techniques we are trying to implement to do trimming for pseudo-Boolean proof. So I'll make a brief introduction about what we want.
Is this recording?
Yes, it says recording.
It says recording. Okay.
Brief introduction about what we want to do. So I won't go about telling you what the PV2 proof is, because I think we know that by now. So for proof trimming, we see the proof as a sequence of constraints. Some constraints are in the formula, and when the solver deduces a new constraint, yes, and each constraint depends on a subset of the formula, so it's deduced from a subset of the formula, and at the end of your proof, you have hopefully a contradiction. Here we're not really interested in SAT instances because we want to trim the unsat instances. Like we could make an argument that maybe we want to have insights about what the solver did when we have SAT instances, but for the most part, we'll focus on unsat instances. So in this proof, like this, we can't see much, but if I write this like this, we can immediately see that for the contradiction, we don't need the constraint C5 that was derived by the solver, so we can trim that away and remove C5 and F4, and we have a smaller proof. And hopefully that would be faster to trim a smaller proof. The problem here is all the blue edges that you see here, we don't have them in most cases. So the goal is for trimming is to find back what antecedents are for like each constraint, which constraint derive each constraint. So that's the main problem for proof trimming. So when we're looking for antecedent for the bold statements like this, it's very easy because this just says take constraint F1 multiplied by 3 at constraint C1. So the antecedent is just the constraints F1 and C1. But for like a RUP statement like this, if we don't have the hints, then we have no other choice than to run the RUP algorithm and to find all the constraints that were used to propagate something and add that to the antecedent set for this constraint. And then we have more complicated rules like the redundant, where we have some proof calls and we can have some interesting things happening. Like for example, if I'm trimming, I'm going from the bottom here. Like, do I need this subproof? Well, do I need constraint C2 in the proof? Maybe I say, okay, no, I don't need constraint C2. So like let's don't use that proof call and that subproof. But then I'm like, okay, do I need this proof call? Yes, C1 is in my small proof. So, okay, I'll go through this subproof and look at the antecedent of this subproof. But here, as antecedent for this pole line, I have C2. So then I have to go back to this proof call to say, okay, finally, I need this proof call. So you have some bookkeeping to do for all the rules that involve proof calls. And we have several ideas of how to manage that. So like the main idea is like to mark them, but conditionally and stuff like that. So when we're doing proof trimming, one thing we can do is a precise deletion, because if we have like this is the antecedent graph for some constraints, when I'm writing the proof on the right side here, I write constraint 1, constraint 2, constraint 3, constraint 4, and when the moment I write constraint 5, I know thanks to my antecedent graph that I can delete constraint 1. And I can write constraint 6, 7, 8, and the moment I write constraint 8, I know that I can delete constraint 2, 3, and 7. So we can make more precise deletions thanks to having all the antecedents for each constraint. And one thing that is common to both trimmer is that we don't want to make the normal RUP algorithm. So like a very basic idea of RUP is like why we don't have contradiction propagate until you have contradiction, and if you don't have then you have a problem with your RUP statement. But here we're going to do what some call cone first RUP, but some other call core first RUP, some other call it marked constraints first, like choose, pick your name. I will call it the cone first RUP. So the idea is like we are going to propagate in the marked constraints first. So the marked constraints are the constraints that we already know we need in the small proof. So each time like we're only propagated in that, and when nothing propagates in the marked constraint, then we're going to propagate only once in the non-marked constraint, and then we're going back to the marked constraint. So in this talk, I will present two tools that have quite different goals. The first one is trimming to have faster proof checks. I think I don't need to say why we want to check the proof faster. So the idea here is that we have three phases. The first phase is the decoration phase, where we're going to produce something called the decorated proof. And this proof knows all the goal of this proof is to have the database available for the trimmer. Because the trimmer is going from the bottom of the proof, we need the database to compute the wrap statements. So we need to, in this first phase, to compute the poll lines, and we need to add the constraints when we delete them. So like, for example, here, when my trimmer is going from the bottom, it says, oh, I deleted, the constraint F2 was deleted. But what was constraint F2? I don't know it. So in the decoration phase, we have to write, okay, the constraint F2 is equal to CZ greater than R. And this is the constraint F2, and we add it to the database so the trimmer can perform all the wrap algorithm. And same for the poll lines, we need to write them somewhere in the database, so we need to compute all the poll lines of the proof. The second phase is the backward trimming. So we have this decorated phase, we have all the bookkeeping for the database, and we go from the contradiction to the top of the proof. We run the pawn first wrap algorithm, we mark all the needed constraints, and we conditionally mark proof goals because we don't know if we're going to need them yet or not. And then we have the compaction phase, where it's the last forward pass. We are writing the elaborated proof, the proof that we can give to KPB with all of the hints. And we know on the third pass which proof goals we actually need, so we can make the marking for the proof goals. We can add the precise deletions I presented earlier. So a few words about that. So if your solver can output the decorated proof right away, then the trimmer doesn't need to make the decoration. That's something you can do, but like, for example, the constraint solver doesn't know what this poll line is. It's just using it as a cutting step. So it's not always available. And same if you have only poll lines, then the proof trimming is easy because you have all the antecedent for free. And secondly, the advantage of this technique is that you can write each intermediate steps on the proof. So you have the decorated proof between step 1 and 2. You have the trim proof with conditional marking from step 2 to step 3, and then you have your small proof. So it can theoretically trim big proofs that would not fit in RAM. So the state of development is the following. So we don't have a very fast working trimmer yet. What we have is the pawn first wrap algorithm implemented, all phases for poll and wrap only. The trimmer is full RAM for now, and you have an option if you want to skip the decoration phase. Berhan is working on the redundance rule, some optimization, then strengthening to core, and finally the file option to trim big proofs. The end goal of this tool is to support the full VeryPB chroma, so we can have it as a tool we can use. To do that, we need some code optimization, because we want this trimmer to be fast, and in the end, we also want PB trimming paper at some point. And now I'll talk about the second idea to do trimming, which has quite different philosophy. It's to compute smaller proofs. So why would you want a smaller proof? The first use case would be to provide a certificate. So maybe you're willing to spend more time to produce a small certificate that is fast to check. Like, for example, the people in cryptography, they love to have certificate of unsatisfiability. And if your certificate is 1 gigabyte instead of 1 terabyte, then I think they're going to be happy. And the second use case is to try. So if you have, you may gain insight on what are problems that are actually the core and SAT part of the problem. The main philosophy here is that we are willing to take more time and resources to trim more, and we should never trust Matthew's proofs because we don't doubt everything. So if I take back my example here, like maybe if I was doing my wrap algorithm on the contradiction, if I think very hard, maybe I could have figured out that instead of doing all that, I could deduce C3 from F4 and then the contradiction. Then I have a much smaller proof. from the original proof, because all these constraints are in the original proof, but I have no small proof for the contradiction. The first thing we don't trust in Matthew's proofs are the deletions. So what can usually happen in proofs, especially for the constraint solver, is that Matthew is going to make a lot of intermediary steps to compute one constraint that is really important. So for example, here he computes like C11, C12, and then he deduces like C1 is the thing I want to deduce. Then he deletes C11, C12, and sometime later on the proof, he makes C21, C22, and deduce C2. And maybe the trimmer can figure out like, if I remove these deletions, maybe I don't need them earlier, and I can use C11, C12 for deducing C1, C2, C3. The problem when you're doing that is that you have to be careful with redundant. So this is an example where a very, very dumb example where I introduce a variable y with a not y greater than 1, then I delete it, then I introduce the reverse. And if I forget about deletion without care, then I have a contradiction here, which is, I introduce a contradiction in my proof, which is like not something I'm allowed to do. So you have to take care of to be cautious. You have to be aware of this. And like if you don't reuse the name and don't do like crazy symmetry breaking stuff, should be okay. In all the subgraph proofs, all the constraints solver proof, like it's okay to remove deletions like this. The main part of what we can do better is trying to make the rep algorithm better. So we had the cone first ID, but I introduced two new things. The first is a heuristic to prioritize the highest constraint in the proof, because if your constraint is high in the proof, it is likely to have less antecedents than if it is at the bottom of the proof. And the second thing is some conflict analysis to try to get the smallest antecedent set for each rep propagation. So it now looks like this. So I have the same only marked Boolean here, but my propagation is now in an ordered set. And at the end here, I update an implication graph where I put for each node that propagated the literal level of propagation and the constraint ID that propagated that literal. That is going to help me to do the conflict analysis. And at the end of my rep algorithm, I will call the mark antecedent from conflict analysis function, the MAFCA function. And there I'm starting from the contradiction, and for each constraint that propagated something, I'm gonna look at the literals that propagated this, and I'm gonna like sort them by my order, my heuristic, and I'm gonna take only the one I need. So for example, here I have some propagation for a rep statement. So each letter is a literal, so A has been set to 1, and then a constraint which just says like from A and B, I deduce that E can be set to true. Yes. And at the end, I have my contradiction at the constraint 5, which is at the bottom here. And what I can see here is that C5 is contradicting because A was true, D was true, and F was true. But if you look at these constraints, you can see that I only need 2 of these for the constraint to be contradicting. So if you allow me to choose them, then I will choose A and D, and suddenly my antecedent set is smaller because I don't need the constraint that produced E, I don't need the constraint that produced H, and so on. And so one idea that emerged from that conflict analysis is, wait, can we do something we call width trimming? Maybe we can change the name at some point. So this is an example of a constraint we have in like the subgraph solver. So sometimes we have lots of variables, and one of them has a big coefficient. And in my conflict analysis, when A, B, C, D, and E were set to false, I propagated 10x, because otherwise the constraint would be falsified. And if in my entire proof, I never use the other variables, then I can say, okay, let's weaken all of them. Let's say like F is 1, G is 1, H is 1, and so on, and replace that constraint by this one, which do exactly the same propagation I need for my proof, but it's smaller, so like we gain some space and maybe some insight on the problem too. The direct problem with this is that we don't have only rep statements, we also have pole lines. And how do I propagate that like red information, the mandatory literals for in each constraint through the pole lines? So let's have this example where I have 3 constraints, 1, 2, 3, and my pole line is just adding these 3. Then it gives the bottom line where my conflict analysis told me that I only need A and X. How do I like propagate this information back to the antecedents? Do I just like say, okay, let's just use A and X in all the constraints and weaken all of them? And here there is a big problem, and this problem is that B appears negatively in the first constraint and B appears positively in the second constraint. So if I weaken B, then the negative literal regarding B will be set to false, and this is not allowed because I would like change the constraint. So what I think we should do is to have this kind of compute all the literals that appear positively and negatively in the antecedent of the pole statements, and then add them to the mandatory literals that we need in this constraint. So in this case, we can only D and E in the first constraint, and in the fifth constraint, I cannot weaken B. And the question that arises just after that is, what do I do when I have saturation division? Yes?
Also, like in your example, you only have one pole statement for if you have many pole statements where each one depends on the next, then you can't do this, right? You have to compute the entire.
I have the red variables are the mandatory set for each constraint, and since I'm doing it backward, I will use like each pole statement only once, so I can back propagate here. So from this one, I know that this is the mandatory set, but if I have another pole statement that uses this constraint and says, okay, actually I needed D, I need to add it here. Yes, so far it's been working on my instances. So maybe we need to think harder about this, because I think that's not the best way we can do that.
It probably works, but I just think it should be expensive, right?
Oh, of course, but I'm allowed to do that because I'm allowed to take more time. Yes, of course, it's very expensive. So I'm also working on some visualizations. They do not fit in the margin. So the problem here is the subgraph isomorphism problem that Karen told you about. So this is the pattern graph, and you have to figure out if this pattern graph can fit in this target graph. So yes or no? And the interesting part of trimming and the width trimming is that this is another pattern graph, and all the red edges and the red nodes have been removed from the proof. So I know that this graph, this smaller graph, is a smaller graph that is the ansat core of my problem. This smaller graph, the green one, does not fit in my target graph. And the problem I have with that is that I know for this instance that the smallest graph you can craft is a triangle. And the trim proof is like still bigger than that. So I think we have more things to do.
Wait, so what you're saying is we have a pattern graph that you want to embed in a target graph.
Yes.
And now let's just construct an example where this big target graph doesn't contain a triangle, but your smaller pattern graph does. And
well, I know for a fact that the pattern graph
does. You're saying this is an example of it. So you would like to somehow, everything should be red here except like a triangle should be highlighted in green.
Yes, that's the thing I would like to have.
Okay, but then this is basically telling you probably that this is not what your solver figured out.
Yes. What the solver did here is it took the highest degree node, 37, and it tried to put it at every vertex of the target graph. And since the target graph max degree is 2, then he was okay. I cannot put 37 in the target graph, so I cannot do that. So yeah. Finally, an idea that we did not implement in a very satisfactory way yet, but maybe we can discuss it, is the justification. So the idea here is that Matthew is going to give me this kind of proof where I have my input formula and he's going to tell me, okay, I know C1, I know how to deduce C1, trust me, but I won't give you the proof because it's very long. And he does that for C1, C2, C3, C4. Then what we can do is call a trimming procedure on that, and then I can get rid of C3 and C1. And then I ask Matthew, okay, now produce the justification for C2 and C4, and then have the the full proof with all the intermediary steps that can produce C2. We can see two main advantages of doing it like this. The first one is that this is a much smaller proof. Like with the assertion, we prevent Matthew from printing very, very large proof. And the second one is Matthew can tell me, okay, constraint C1, I know that the justification is very easy, like it's a very small justification. But constraint C2, please, I beg you, don't use that. And this I can put in my heuristic, like in my converse with heuristic, I can okay, try to use C2 only if you really, really. And the big question that is here is where the justification algorithm should live and what should it look like, because it needs to know some stuff about what was happening in the CP solver at some point. That's, I think, that's the main question of this skeleton type of proofs.
I mean, it's worth commenting just in this context that apparently in satisfiability modulo theories proof logging, this kind of having a proof skeleton and then trimming and getting a slightly more detailed proof, but still a skeleton and then trim again is apparently absolutely key. Like doing this in several steps to defer, like you really only expand the proof when you know that I really need the details.
Yeah.
So it stands to reason that this might also be very important for constraint programming.
Isn't it different that in SMT the problem is writing proof? The steps are very big.
But that's sort of the problem we have as
But
well.
also you also have.
But some of these assertions will expand out to
Okay.
potentially a quadratic sized.
Because on the slide you always have small assertions, so never sure how big they really are. Okay, so they are big. Okay, so
They always fit in the margin.
How do we know that C2 doesn't require, say, F2 and C1?
This is why I
That's
annotated
the
assertion.
Okay, we're annotating.
Yeah.
Okay, yeah.
Yes, that's very important. So state of development of these tools, so I have first work with conflict analysis heuristics. I support full run predictions and optimization, and I have a full run trimmer. I have 3 terabytes of RAM. So the limiting factor here is me being lazy, not the RAM. I'm working on width trimming, so we're trying like different ideas. Maybe we can visualization to about the problem, and later maybe we dive deeper in justification. And the end goal of this trimmer is to get proof as small as possible to see what we can get. Get satisfactory problem inside in small proof, and the problematic part of this sentence is satisfactory. What is a reasonable explanation? When does an explanation becomes a human readable explanation? That's open to debate, and of course we want a PB trimming paper at some point too. So for a conclusion, I don't have any clean benchmark to show you. I only have some instances with comparisons that are not very fair. So like I'm comparing potatoes and tomatoes, it's not very good, but like the expected result should be like this. So we have very PB, the size of the instance here is 5 megabytes. The fast PB, like it's the fast trimmer, is reducing the instance size. So here it's bigger because it's producing the elaborated proof. So we have all the hints, that's why it's bigger here. And then the small PB is my trimmer, which spend more time to figure out, can we have very small instance. And the times are here, so very PB 44 seconds, fast PB is faster, and small PB is longer, but one interesting thing here is that this very time is the time that very PB took to check the small proof. So I would say that's the lower bound we can expect from this instance if we figured out how to make a very, very fast and efficient trimmer. So this is the best world where everything is very nice, but then I have two instances where the small PB instance is not the smallest and the fast PB trimmer, it's not the fastest. So yeah, that's the real world where some things don't happen like you want them to do. Then I have some real weird instances. So if you look at this one, the last two, both of them are reduced to 400 kilobytes type of proofs. Both of them are checked with 44 second-ish. But here, the small proof is checked in 0.8 seconds, and the small proof is checked in 9.9 seconds. Because like I looked at both the proofs, and they look quite similar, so I can't explain why this one is 10 times slower to check, even if they have the same size. Like we have lots of variability between the instances. And I have two more. So this is like an instance, but it's not that big. Like 18 megabytes is reasonable, and the small proof is 500 kilobytes, but it still takes 30 seconds to check. And then like I have another extreme example where the fast PB proof is like 100 megabytes bigger than the original PB proof. So yes, to take that with a grain of salt. That's because of the elaboration. Like the hints are enormous, and it makes the proof like extremely larger. And yeah, so don't take these as real comparisons between the tools. Like we need to work much more on the fast PB trimmer and the small PB trimmer to have and to produce real benchmark to compare comparable. And I think that's all.
Question for Arthur?
But so does that mean that if I take a maxhat instance, you will I mean the maxhat solver will find intermediate things, and basically after trimming you will just have one line which is the optimal solution, and then I have an answer, right?
Yes.
Which means that you are going very far away from what the solver actually did.
Yes. And that's I think if we have a trimmer with lots of fancy options, one option should be okay, stick to what the trimmer did to have like more debugging purposes of trimmer, because here we are allowed to do lots of crazy stuff.
The answer proof would still probably be fairly non-trivial.
Yeah, no, but it's kind of interesting because you kind of change paradigm. I mean, it would be a different SAT solving paradigm, max SAT solving paradigm, which I find an interesting thing that the optimal solution is to something different.
Marcus?
If your goal is to get like the smallest proof that you can in reasonable time, have you thought about firing up like a mid solver to minimize the like number of antecedents you get in a rough step, or do like a sliding window over multiple ones?
We can do that for the poll statement, because you have like adding linear constraint to get another one, and we can minimize the number of antecedents for that poll constraint. So we can fire LPs. I'm not doing it currently because it's like very costly and it didn't trim any things so far in my instances. But to do that on the whole proof, I don't know if that's.
No, you could do a couple of lines at once, right? You could take like 5 rough statements and try to minimize the antecedents of those. I think you could formulate this.
Oh, okay. See it. But then would I need to compute all the possible antecedents for this two?
I don't know, but I would imagine that you could formulate this as a.
Okay.
Me project.
Yes.
I'm pretty sure that Stefan Seider has some line of work on this, so I think that they call it proof minimization. But of course, they do it on clauses and the resolution proof system, right? So. Yeah.
But what Stefan does is, if I'm talking about the right thing, it's they formulate finding the minimal proof as a SAT problem. So that's.
It's much beyond what we're trying to do here, right? But maybe some relaxation on that problem can be suitable. Right?
But I don't think you have to do the whole proof at once. I think you could.
No, I agree. I agree.
Just one comment also that I don't know if this would make any difference in practice, but if you're trying to really minimize the proofs, one other thing you could think about when you're propagating is maybe you should prioritize which constraints you try to propagate on first. For instance, maybe you could get the same propagation from a bunch of clauses, or maybe you have a strong at most one constraint, which is just a single constraint, and if you try that one first and see if that propagates, then maybe that could give that single constraints could give many propagations that would replace all of these clauses. If you're careful, prioritize your propagation in order of strength of constraints, you could hope to mark fewer.
So we try both options and take the one with the fewest entities.
No. When you're doing your propagation, you're looking at constraints in some order.
Yes.
Okay, so you could imagine having, and right now you probably just have a queue, first in, first out. You could imagine having a priority queue.
I have a priority queue.
In terms of, and prioritizing in terms of what?
In terms of the highest constraints first. But maybe you can give me another better order.
Yeah, so okay, so maybe that, yes, another possible thing to sort on, but could potentially be again that you would prefer stronger types of constraints over less strong.
How do I know what is a stronger type of constraint? I can ask Matthew and he will tell me.
Well, you could say, you can, that's an excellent question, and I don't know that there's definitely, I would say, for instance, if you know that x1 plus x2 is at least 1, that's one choice of a constraint, or x1 plus x2 all the way plus up to x10 is at least 9, and I say the second constraint is really strong.
Okay, yeah.
And there's some, and we were also playing around with this in other settings, but we don't have any clear-cut connections. Okay, so should we thank Arthur again?